In this video, we're going to discuss simple neural networks. We'll do an intro to neural networks in PyTorch with one hidden layer, and we'll know what that means very shortly. And then we'll discuss how more neurons allow you to build more complicated functions and allow you to classify data that you couldn't usually classify before. So it's helpful to think of a neural network as a function that approximates another function. So we have our function in red, and we can use the neural network to approximate that function, and we'll draw the output of our neural network in blue. So let's go over the classification case. So in the linear case, we used the color to denote the class, and we said red would be 0 and blue would be 1. So for neural networks, it's helpful to think of it as decision function. So we'll just elevate the points, and anything from the region -1 to 1, the function should output a 1, and everywhere else it should output a 0. So let's compare linear classifiers to neural networks. So we have our data points, and in this case, you can see you can use a line to separate the two classes. But let's see what happens if we add a few more data points. So we want to approximate this decision function, and we can use this line, but everything in this point is misclassified. And let's see what happens when we apply a sigmoid function to the line. As you can see right now, it looks like a function that maps everything in this region to 0 and everything in this region to 1, but it doesn't look like the function we want because everything over here is misclassified. So let's try another line. If we use this line, everything in this region is misclassified. If we apply a sigmoid activation function to it, we can see that all these points are misclassified. But let's see what happens when we use both those functions to classify the data. Something interesting happens when we use the output of the sigmoid functions for both lines to classify the data. So we have the output of the first sigmoid function, and we subtract the second sigmoid function, and we get a function that kind of approximates the function we want to copy. And if we apply a threshold to it, we actually get the identical function. And this is what neural networks do. So the math for neural networks can get a little complicated. So we usually use diagrams to represent the functions. And these points over here represent the lines, or the linear classifiers, and they have an output. And then we apply the sigmoid function to it, and we get an output like that. And then we have another set of a linear function, which represents adding those two functions together, and then we get an output. And then we apply another sigmoid function to it. So just a note, we're going to refer to the sigmoid function as an activation function, because it turns out there's other functions we can use other than the sigmoid function. So this part of the neural network is called an artificial neuron, because it emulates how neurons work. And we divide our network into layers. So this is called the output layer, and then this layer is called the hidden layer. So let's see the output of the linear units. So we have the linear units, and we'll map it to Z1 and Z2, and we can plot them out in the 2D plane. And these points in the 1D plane get mapped to these points in the 2D plane. These points in the 1D plane get mapped to these points, and finally these points get mapped to these points in the 2D plane. Something really interesting happens when we apply an activation function to it, and we get something that looks like this. So these points in the 1D plane get mapped to these points in the 2D plane. These points in the 1D plane get mapped to these points in the 2D plane. And these points in the 1D plane get mapped to these points in the 2D plane. And if we look at the output of A1 and A2, we can actually use a line to separate the data. And this is what the output layer does, basically. So let's try to create one of these networks in PyTorch. So here's our neural network class or custom module. And in this case, dn will equal 1. And that basically says we have a one-dimensional input represented by that variable. And then we'll have two hidden units denoted by the h. And then these two hidden units will be the input to the output layer, So we have h and d out will equal 1 in this case. And in the forward step, we'll just apply a sigmoid activation to the first layer, and then we'll apply a sigmoid function to the output. And that's it. So it's helpful to use matrix operations to represent it as well. So we can represent the first linear layer with matrix algebra. And we have one input dimension, and then we have two outputs, and the two hidden neurons are represented by these two guys over here, and they have two outputs. And then we apply a sigmoid activation to each output, and then we get two outputs. And then those two outputs are used in the input to the next layer. And of course, for this to work, the green parameter vector has to have two parameters. And then finally, we apply a sigmoid activation function to the output. So here's when we create the model, here are the actual parameters we use. And then the 1 will represent this value over here, and then the 2 will represent these two parameter vectors and the two biases. And then the two outputs will be put as an input to the output layer, and we'll get one output. And then we'll apply an activation function to it. And of course, we can make a prediction. So I always get the terminology confused, so let's do a couple of examples to clarify it. So in this model, we have one hidden layer and 4 neurons. In this model, we have one hidden layer and 10 hidden neurons. And in this model, we have one hidden layer with 2 hidden neurons. Another way to build neural networks is using the sequential module. So here's a sequential module, and we have one input and 2 hidden layers. We apply the sigmoid function to it. Then we have the output layer. Then we have the linear unit for the output layer, and then we have the sigmoid function. In both cases, we can make a prediction as follows. So let's see what happens when we add more hidden neurons. So as these pictures get complicated, what we're going to do is we're going to combine the output of the activation function, or sigmoid function, and the linear unit, like that, and we'll put the parameters as follows. And we're going to just forget about the bias term. And also, as these models get more complicated, we're going to actually get rid of the parameters, just so it's easier for me to draw out. So let's do an example when we have a one-dimensional input, and then we have 6 hidden neurons. And let's see if we can use a neural network to approximate this function. So anything in the region between -10 and -5 should be mapped to the class 1. And anything from the region 5 to 10 should also be mapped to class 1. And everything else should be mapped to 0. So let's see how we can use this simple network with 6 hidden neurons in its hidden layer to approximate this function. And don't worry, we'll do the training later. So we're going to look at the output of this neuron multiplied by this parameter. And let's do these first 3 units first. So the output of this term looks something like this. The output of this term looks something like this. And the output of this term looks something like this. And I know this final term doesn't do much, but it seems to work better if I add it. So the output looks something like this. So let's see what happens when we add the outputs of these 3 neurons multiplied by these 3 parameters. So the output of this neuron multiplied by this parameter looks something like this, and we add it to the output of our first 3 neurons, and it kind of looks something like this. Then we take the output of this neuron, multiply it by the following parameter, and add it to the output of our last 4 neurons, and we get something like this. And as you can see, our function is kind of looking like the original function. Finally, we'll take the output of this neuron, multiply it by this parameter, and add it to the output of our other neurons, and we get something that looks like this. So I thought I made a coding mistake, because our output looks like this. But when we apply the final nonlinear sigmoid function, we get the correct output. And that's it. A neural network is just building a function out of simpler functions. So let's train a model So we use our BCE loss because our output is a logistic unit. We'll create some data set and a training data loader object. We'll create a model, and in this case, we'll have 2 neurons in our hidden layer. And we'll create our optimizer, and we'll use a function to train the model. And that's it. So now we'll go into building more complicated neural networks.